And so at the end of our last lecture, we said, well, we can use the actual confidence interval that we can construct to draw conclusions or make a rejection decision, right? And we went over these two statements here. We said that a 95% confidence interval, and actually it can be any percent confidence interval, that contains 0 is equivalent to failing to reject the null hypothesis. And then if it does not contain 0, that means 0 is not a plausible value, which means I'm not expecting the 0 here, so then I'm going to be rejecting my null hypothesis. And so we went over this example and saw how we can draw conclusions there. That's where we left off last time. And so that is it with our hypothesis test for a non-directional alternative hypothesis. And so now that we already know that, let's talk about some of the errors or mistakes we can make. All right? So when we reject the null hypothesis, we can reject it when we should reject it, or we can reject it when and make an error. All right? And the error that we make when we reject the null hypothesis is known as a type 1 error. And so I remember this by saying a type 1 error is a rejection error. The only way that we can make it is if we reject the null hypothesis. All right? And remember, we do that when our p-value is less than or equal to alpha. It's an error because it says if we reject H naught when it is in fact true, then we're making actually that type 1 error, right? We shouldn't reject the null if the null hypothesis is actually true. Now, we'll never know this in real life, whether the null hypothesis is true or false, but we're saying here a type 1 error is rejecting a null when it is in fact false. Sorry, when it is in fact true, all right? The actual probability of making a type 1 error is denoted by the symbol alpha. Now, we've been talking about the hypothesis test all week, and we mentioned alpha. Can someone tell me what alpha represented? What do you say, Casey? What did alpha represent before? You know, Aaron, what did we say alpha was when we were doing hypothesis tests? Lydia? Your significance level, right? So we actually set, whenever we do a hypothesis test, we set the type 1 error rate, all right? We're saying that there's a 0.05, when we say the significance level is 0.05, we're saying that we have a 0.05 probability of making a type 1 error, rejecting the null hypothesis when we should not reject it, right? That means the null hypothesis is true. In symbols, if you wanted to write your type 1 error as a probability statement, it's the probability that we reject H naught given H naught is true. All right? All right, that's a type 1 error. A type 2 error is not a rejection error. It's the other decision that we make, right? When we do a hypothesis test, we're either going to reject the null or we're going to fail to reject the null, all right? And remember, we fail to reject the null when our p-value is greater than that significance level alpha, all right? So if we fail to reject the null hypothesis when it is in fact not true, that means it's false, we're making a type 2 error. All right? Now, we hadn't talked about this yet, but the probability of making a type 2 error is given by the Greek letter beta. All right? And we've not mentioned this before. We would have to calculate beta if we really wanted it. But in probability notation, it would be the probability of failing to reject the null given that H naught, the null, is false. It's not true. Okay? And when the null hypothesis is false, we kind of automatically assume that the alternative is true. So another way that you can write this probability statement is the probability of failing to reject our null hypothesis, given that that alternative hypothesis is true. All right? So those are the two types of errors we can make whenever we do hypothesis tests. Hopefully we won't have that happen. But if we do, alpha is the probability of making a type 1 error, and beta is the probability of making a type 2 error. All right? So that's the two types of errors we have here. Now, if you look on the next page in your notes, it has a table of all of the possible outcomes when you do a hypothesis test. Okay? In almost every statistics class that does hypothesis tests, they review this table here, so I'll review it with you guys. All right? So in this table, we have a couple of things happening here. So we have our decision whenever we conduct a hypothesis test, right? So we have our decision here. We're either going to reject the null or fail to reject the null, right? This is what we do in practice whenever we do a study. And then we have our true situations, right? These are unknown things, right? But this is the truth. Either our null hypothesis is going to be true or our null hypothesis is going to be false. All right? And when our null hypothesis is false, it's the exact same thing as saying your alternative is true. All right? Now, when we reject the null hypothesis, when that null hypothesis is in fact true, right? We don't want to reject the truth, right? That's the case where we make a type 1 error. So I'm going to fill this box with type 1 error. That's the mistake, right? If our null hypothesis is true and we end up rejecting, we've made a type 1 error. If our null hypothesis is false, so the null is false, I want to reject it, right? So if the null hypothesis is false and we reject the null, then we've made a correct decision. So I'm going to fill this box with correct decision. So whenever we reject the null, we're either going to have a type 1 error or we're going to make a correct decision, right? All right, similarly, failing to reject, all right? We don't like to say accepting the null hypothesis, but if our null hypothesis is true and we fail to reject, that's a good thing, right? We've made a correct decision. But if we fail to reject the null and our null hypothesis is actually false, the alternative is true, we always want to reject here when an alternative is true, right? So if we don't do that, we've made a type 2 error. All right? And so these are the possible outcomes whenever we do a hypothesis test. We're either going to make a type 1 error or a correct decision when we reject the null, or we're going to make a correct decision and a type 2 error when we fail to reject the null hypothesis. All right? Now, with that being said, there's one additional term that's going to be very important whenever you try to do a study of your own. All right? And it's known as statistical power. A lot of people just say power. But it's statistical power. Okay? The power of a statistical test is just 1 minus your type 2 error. So 1 minus beta. 1 minus the probability of making a type 2 error. All right? It is the probability of rejecting the null hypothesis given that it is not actually true. All right? It's the probability of rejecting the null hypothesis given that it is not true. All right? That's what we want to happen, right? So the power aligns with this starred correct decision here. So we can say that the power, or 1 minus beta, is the probability that we reject H naught given H naught is false. Statistical power is a good quality of a hypothesis test because we want to reject H naught when it's false. So ultimately, we want power to be a large probability. Okay? We want the probability of rejecting a false null to be high, to be large. Okay? So, this is similar to something that we discussed earlier in the semester when we were talking about diagnostic tests. All right? Does anyone remember any of the terms we use with those diagnostic tests, right? Probabilities of a test coming out positive or the probability of a test coming out negative. What were some of those terms associated with that? You got one, Casey?
False negative.
False negative, false positive, right? True negative and true positive. What are some other terms we talked about? I'm looking for two terms. They both start with the letter S. Sensitivity and specificity, right? It turns out that for a hypothesis test, this power is very similar to the sensitivity of a test, right? Remember, sensitivity was like the probability of the test coming out positive and detecting that you have a disease, given that you do have a disease, right? Well, this is a similar thing, right? It's the probability of detecting that the null hypothesis is false, given that the null hypothesis is false, right? So your power, which is why we want this to be a large probability, it is very similar to the sensitivity of a diagnostic test. All right? It's basically the same concept. That 1 minus beta and the type 2 error, they have to do with a lot of different things of your specific experiment or study that you're doing, right? There's actually a whole section in our textbook on statistical power. That's section 7.7, and we're going to get there later. All right, it depends on your sample size, how big of an effect you expect to see in your population, and some other factors. And so we're going to revisit the statistical power here, but we're introducing it since it's related to your type 1 error. All right? So we won't be calculating power or anything like that, but we do want to know what are the impacts of making a type 1 and a type 2 error. And so I have an example here where we have a study that's conducted on cancer treatments. And so as we probably all are aware, chemotherapy is a standard treatment for a certain cancer, all right? And in this study, it's for a certain cancer. Suppose we conduct a clinical trial to study the efficacy of supplementing chemotherapy with immunotherapy, right? And immunotherapy is the stimulation of the immune system. So patients are either given just regular old chemotherapy, and then other patients in another group are going to be given chemotherapy plus the immunotherapy, all right? So we have a clinical trial here, two groups getting different treatments, all right? Now, in this study, we have these two hypotheses here. They're not written in terms of mu1 and mu2, but when we've been writing our hypotheses, we've also written them in this way here, right? So the null hypothesis here is that immunotherapy has no effect on survival. That's similar to saying whatever we're measuring, mu1 equals mu2, right? So if we're measuring the progress of cancer by looking at maybe the number of cancer cells or something like that, when it says immunotherapy has no effect, the mean for the group with just chemo would be equal to the mean of the group with chemo plus immunotherapy. All right, they're equal, then that means the immunotherapy is not doing anything, right? And then my alternative hypothesis, remember we call this our research hypothesis, which is what we're usually interested in, is that immunotherapy does have an effect on survival. So this is equivalent to saying mu1 does not equal mu2. All right? Just given to us in words. So we want to identify a type 1 error in this context here. What does it mean to make a type 1 error? Well, if I think about it and I go back, I'm going to go back up to my chart a little bit. A type 1 error is the probability of rejecting the null given that the null hypothesis is true. And whenever we reject the null, we conclude the alternative, right? And so in identifying the type 1 error, that is equivalent to concluding that immunotherapy does affect survival when it actually does not. So it's concluding that it actually has an effect, concluding that immunotherapy has an effect, even though it does not, right? Remember, it's a rejection error, right? So when we reject the null, we conclude the alternative, and the alternative here is that immunotherapy has an effect. Well, we've made an error, so it actually doesn't have the effect, right? And so the consequences or the complications from that or implications from that is that we may give patients, all right, we may give patients an ineffective treatment. All right, and so we don't want to make a type 1 error here. So that's your rejection error. We conclude that immunotherapy does have an effect when it actually doesn't. And if we draw that conclusion and move forward after that study, we may give the patients that ineffective treatment. So that could potentially lead to more death, right? Less survival. So that is a very serious error. All right? I want everybody to try to identify the type 2 error in this example. Remember that this error comes from failing to reject your null hypothesis. This error comes from failing to reject. That means we haven't gathered enough evidence. But failing to reject when we actually shouldn't fail to reject. All right, would someone like to say what they think is the type 2 error in this example? What do you think, Alexander? Okay. Olivia, you have an idea? All right. So when we fail to reject the null, right? In general, when we fail to reject, we say there's not enough evidence to say that this thing right here is true, right? So when we do that, we're kind of saying that the null hypothesis might be true, right? We just haven't gathered enough evidence, right? So what we would do in a type 2 error case is we may conclude that immunotherapy has no effect when in reality it actually does, all right? And so a type 2 error, we might think that this is true. We might conclude that this is true. So the type 2 error may be that concluding that immunotherapy has no effect or effect, I always get those mixed up, on survival when it actually does. Okay? And so that's also an error that we don't want to make, because in this case, patients may miss out on an effective treatment. All right? So we don't want to make that mistake either. But that might be less detrimental than this one here. Like giving them something that they're thinking is going to be effective and it's not going to do anything for them that can highly impact survival. This one may impact survival, but you might say, okay, well, let's try some other treatment, right? And so you want to be able to read a study and be able to identify in a similar example, the type 1 and type 2 errors. All right? Any questions with that example? All right. Remember, these are the practice problems in the book, and I think I placed the practice problems in your Blackboard. So if you need the solutions, you're doing those problems in addition to your homework, the solutions are on Blackboard in the Chapter 7 folder. So remember, you should be doing these between classes, and let me know if you have questions in between, right? All right. That is it with section 7.3. We're going to go to section 7.5, and we're going to pick up with one-sided or one-tailed test, all right? So once again, when we were doing our null and our alternative hypothesis before, we had mu1 equals mu2, and my alternative was mu1 does not equal mu2, right? This is a non-directional test, all right? Well, there are some hypotheses where we're assuming or we're thinking that one population mean would be greater than the other population mean, or one population mean may be less than the other, right? And so it says, often in scientific studies, our hypotheses have a direction attached to it, right? Either a greater than or less than. And so in this example, it says in a sleep aid study, we may want to show that a certain drug works better than an existing drug, right? Then our alternative hypothesis, well, if it's a sleep aid study, it's to help people sleep longer. So our variable of interest will probably be the length of sleep, the length of time an individual sleeps per night, right? And so let's say that we're giving one group the new drug, then we would expect the mean in the population for that new drug, so I'm going to do mu with a subscript nu, to be greater than the average hours of sleep that patients with the old drug may get, or patients with a placebo may receive. Okay? Notice that alternative has a direction. We're using a greater than here. All right? The second example, we have a cholesterol study. We may want to show that a certain drug lowers cholesterol, all right? Well, if it lowers cholesterol, then the mean for the individuals who's getting that drug should be less than, they should have a cholesterol that's smaller on average compared to people who, let's say, may get a placebo, right? And so here I have a less than as my alternative hypothesis. Okay? So instead of calling t-tests with alternatives that use a less than or a greater than symbol non-directional, they now have a direction. Okay? So sometimes these are called directional. Sometimes they're called one-sided or one-tailed t-tests. All right? All of those terms are synonyms, right? So if you see them, we're talking about a one-tailed t-test, and the alternative is either going to be a greater than or a less than. The alternative would not be not equal to. Okay? Now, the null hypothesis for these tests will be exactly the same. For us in our course, our null hypothesis is always going to be equality, all right? And the alternative is going to be some kind of inequality, either not equal to or, as we see here, less than or greater than. So since our null hypothesis is still the same, our test statistic is the same, all right? And just as a review, remember our test statistic was y bar 1 minus y bar 2 divided by the standard error of the sampling distribution of the sample mean, right? Or the difference in those sample means. So we have the same exact test statistic. And remember, our test statistic, remember, that's a measure of how different those sample means are, right? It's a measure of how different those sample means are under the assumption that our null hypothesis is true. Well, when we go to calculate our p-value, when our alternative is mu1 minus mu2, I'm just going to not do the minus one. I'm going to do the other way. Mu1 is greater than mu2. In order to calculate our p-value, we go to our t distribution. Now, let's think here, all right? If we talked about this last time, I believe. If mu1 is expected to be greater than mu2, right? That's our educated guess. When we go to our sample, right? When we go to our sample, we expect y bar 1 to also be greater than y bar 2. We should see the same result in our sample data. If this is our alternative, this is our educated guess, right? So in general, if we're going to do an alternative hypothesis like that, we would expect this to occur in our sample. The sample mean 1 would be greater than sample mean 2, right? Is everybody with me? All right. Now, if this is the case, then what do I know about the value of my test statistic? All right, and my test statistic is up here. If y bar 1 is greater than y bar 2, what do I expect my test statistic to be? Say it again. Positive, right? Because when I do y bar 1 minus y bar 2, the numerator is going to be positive, and that denominator is always positive, right? A positive divided by a positive is a positive. So I know my test statistic should be over here most of the time, all right? And remember, your test statistic is the probability of getting this test statistic or one that's more extreme. And more extreme would be in the greater direction. So my p-value is going to be this shaded area here. All right, so it's the probability that of all the possible t-values I can get, remember, I know you probably wonder sometimes why sometimes I capitalize the y and lowercase, have a lowercase y. Lowercase is for the values and then uppercase is for the general statistic, right? So the probability that of all the possible test statistics we get is going to be greater than the test statistic that we get in our data. This is more general. This is the specific value we get from our data set, all right? All right, that's what our p-value represents. And I'm going to be a little extra here, given that our null hypothesis is true. All right. Just remember, this p-value is this shaded area here. It's in the right direction because we're having a greater than alternative hypothesis. All right? As you probably can guess, if our alternative hypothesis is less than, mu1 is less than mu2, if that is the case, we expect y bar 1 to be less than y bar 2. That's an expectation based off of our guess of our alternative, right? And if that's the case, my numerator up here will be negative. The denominator is always positive. A negative divided by a positive is a negative. So my test statistic should be on this side of 0, okay? And so since my p-value is always the probability of whatever possible test statistics we may get, we get one that's smaller than the one that we obtain in our sample. That means this area under the curve is my test statistic. My p-value. So when you have a greater than inequality, you're going to shade to the right of your test statistic to get your p-value. When you have a less than inequality, you're going to shade to the left. That's all you want to remember here. Now, sometimes people get a little nervous with that less than and that greater than and shading to the left and to the right. Okay? Because they get nervous about the size of the p-value. So I'm going to skip over this. We're going to do this stuff in R, and I'll come back to this. Yes?
Why is there a little TS? Why is there a big TS?
All right, it's a generalization of all the possible t values you can get, right? We're focusing on the ones that are greater than the one that we obtain based off of our data, and that's the lowercase one, okay? So in our textbook, we use an uppercase for like a generalization of a variable, and then the lowercase is the actual computed value from your data set, okay? All right. And if I look at that stuff that I wrote up there, I didn't finish the conditional probability here. It's always sitting in the background, given that H0 is true. All right. So, how many of you have read your textbook in section 7.5? Y'all read before class, right? So when you read your textbook, they're going to tell you about a two-step process of conducting these types of hypotheses tests here. All right, and I was a little extra here in writing this piece here that says we expect y bar 1 to be greater than y bar 2. That is not a for sure thing that's going to happen, all right, in that case. And I wrote y bar 1 is expected to be less than y bar 2, all right? I want to write some extra notes down here. So let's say we have our null hypothesis, mu1 equals mu2, and our alternative hypothesis is mu1 is greater than mu2. Let's say when we get to our data set, y bar 1 is less than y bar 2. Okay? So this is a scenario. This can happen. I want everybody to graph the area under the curve that will represent our p-value. That means you're going to put your test statistic either on this side or that side, and you got to shade in a certain direction based off of that alternative hypothesis there. So fill this graph with what we think would be the p-value. And I'm going to remind us that our test statistic is that quantity there. Anybody filled it in? Is my test statistic going to be to the left of 0, representing a negative number, or is it going to be on the right of 0, representing a positive number? What do you say, Tara? A negative, right? Because my test statistic is based off of my sample data, right? And if y bar 1 is less than y bar 2, right? That means when I do that subtraction in that numerator, it's like doing 1 minus 2, right? It's going to be a negative value. So my test statistic is going to be somewhere over here. I don't care what value it is. I just know it's negative. Now, am I going to shade to the left to get my p-value, or am I going to shade to the right to get my p-value? What do you say, Aaron? To the left? Why do you say left? All right, because it's a negative value, right? So what tells me which direction I need to shade? What are you going to say, Alexander? Your alternative is always going to tell you which direction to shade, right? And so since my alternative says greater, I want to look for this value and values that are greater than it, right? So I'm actually going to shade in this direction here. This is kind of conceptually difficult, but that's what happens here, all right? Now, I don't know what value this p-value is, right? But I know that this shaded area is more than half of the total shaded area, right? Because it's on the left of 0. 0 is the line of symmetry. So this shaded area is more than 50% of the total area under the curve. And that's what your p-value is going to be, right? So I don't know what the value of my p-value is, but I know that my p-value is going to be greater than 0.5. Now notice here, I'm saying 0.5 because it's more than half of the area. Half of the area shaded to the right. We have more than that. All right, this is not like the significance level 0.05. Don't confuse these. I'm saying greater than 0.5 because it's more than half of the shaded area. If I get a p-value that large, I'm never going to reject the null hypothesis, all right? And so I already know that this is going to be my result. I'm going to fail to reject the null hypothesis. So without putting any data into RStudio, without getting the p-value results, I know that if my alternative looks this way, but my data look this way, they're opposite, they're in opposite directions, I know my p-value is greater than 0.5, and my result is that I'm going to fail to reject the null. Okay? In this case here, we say that when we see this, we say our data deviate. What's a synonym for deviate? Huh? Skews. What's another one? Our data, it's a little off, right? Our data differs from our null. This is pretty much always going to be the case, right? It's unequal to the null, but in the opposite direction compared to our alternative hypothesis. All right. And when that is the case, I'm not going to run any test. I automatically know I'm going to have a very large p-value, and I'm going to fail to reject my null. All right. The opposite happens. When we go in the opposite direction. So we'll put this in the notes really quickly. So let's say that this is my hypothesis test that I want to conduct. And when I look at my sample means from my data, I see that my sample mean from group 1 is greater than my second sample mean, right? So when I get my test statistic, my test statistic is going to be a positive value because y bar 1 is greater than y bar 2. So that means that numerator is positive. But this alternative dictates which area or which side we're going to shade to get our p-value. So instead of shading to that right tail, we've got to shade to the left because our alternative hypothesis says shade to the left. All right. And in that case, we can see that our p-value is large, right? That's more than half of that area under that curve. So again, our p-value is greater than 0.5. Our alphas are what we usually compare our p-values to, and they're going to be always small numbers like 0.05 and 0.01, stuff like that. So we're always going to have enough information to fail to reject our null hypothesis. All right. So if you read your textbook, they say